Nanocellulose is characterization of nanocellulose from citrus oils. Nanocellulose is a relatively inexpensive, highly versatile bio-based renewable material with advantage properties including the biodegradability and non-toxicity. Numerous potential applications of nanocellulose is its use for the preparation of high performance composites have attracted most attention from industry, owing to low energy consumption and the addition of significant value. Nanocellulose extraction from agricultural waste is one of the best alternatives for waste treatment. This is the scanning electron micrograms of citrus waste biomass (CB) before enzymatic treatment, and simple pretreated with sodium hydroxide and sodium peroxide and pretreated in gentle enzymatic action. Scanning electron micrograms showing hydrolytic effects. In this study, the enzymatic treatment also a marked effect, especially on fiber bundles that became detached from the other bundles, resulting in the unstructured independent fibers. These fibers with diameter of approximately 600 nanometer are present in some areas of the sample. More accurate size determination in the important questions to be answered by future work, considering the reducing the concentration dropped onto the holder. Cellulosic nanofibers have rod-like structure with the average length 458 plus minus 150 nanometer and a width of 10 plus minus 3 nanometer, generating an average aspect ratio of 47 plus minus 18 nanometer, which is considered high. However, generally, microbial and enzymatic treatment of cotton and sugarcane fibers produce nanocellulose aspect ratios of 43 plus minus 13 and 55 plus minus 21 nanometer respectively. These cotton nanofibers exhibit average lengths of 120 plus minus 36 nanometer, and sugarcane bagasse nanofibers have lengths of 255 plus minus 83 nanometer. This is the after of the raw citrus waste biomass. The cellulose profile common to both products and denote the intramolecular hydrogen bonding between the hydroxyl groups on C2 and C6. The pyranose ring 30, 3330 per cm and CS2 symmetric bending at C6 1410 to 1424 per cm. The CS2 wagging bending at C6 1318 per cm. The COS in plane bending at C6 1203 to 1205 per cm, and COC motion of beta glycosidic linkage 1102 to 1105 per cm and 1054 to 1056 per cm. In the carbonyl stretching, the account for 1734 and 1605 per cm. To show stretching vibration of hemicellulose at 1250 per cm, Another significant structural vibration noted related to stressing involving COC and CCS at C5 and C6 that is observed at 893 to 902 per cm, while the enzyme-treated materials presents the characteristics band of beta-glycosidic linkage between the glucose units at 809 99 per cm. The chemical treated materials lacks these bands and shows the additional vibration, higher wave numbers 990, 968 and 940 per cm. The band around 1375 per cm is attributed to CS bending in cellulose with high crystallinity index, whereas the band around 2900 per cm is characteristic of aliphatic CS stretching, hemicellulose and cellulose. This is the XRD of citrus waste biomass. The core corresponds to 16.4 degree, peak 101 plane, which can be separated into amorphous and crystalline portion of deconvolution, whereas the highest peaks at 22.14 degree 002 plane is typically used in the calculation. Citrus waste biomass in the treated materials, the peak intensities, the crystalline cellulose peak 22.4 increase with the increased number of 22.4 increase with the increased number of process steps. Minimum intensity between 002 and 101 peaks. The intensity of amorphous region between 16.4 degree and 18.0 can be attributed to enzymatic hydrolysis, while the crystalline 002 region showed a negligible variation in the signal intensity. This is the NMR of nanocellulosic fibers, citrus waste biomass. C13 NMR reveals that the vibration C4 and C6 areas, the C4 areas specially employed. The C4 peaks 89 ppm is attributed to ordered structure, whereas the C4 peaks at 84 ppm assigned to a less ordered fibril surface. Integration of total C4 areas correspond to 80 to 93 ppm. The region of downfield side 87 to 93 ppm is the principal contributor to the crystalline phase of the cellulose structure. C2, C3 and C5 overlap in the 72 to 76 ppm region and C6 assigned to 62-65 ppm region. In a split similar to C4 and C1 is at 105.4 ppm in cyclate signal. The ratio of C4 crystalline areas at 87 to 93 ppm and the total line fit area is spectrum. This is my reference. Thanks for watching and thank you for your patience. That is now. Bye bye. See you again.